started. But I think it's actually nevertheless a good idea. I mean, if you can kind of like ask me, hey, Dr. Pradanovich, do you see the recording going on? I think that'd be a great, just to double check that the recording is being set. All right, let's get back to our heat transport. So I'm going to share, and also if I don't share the screen, please remind me. Same things that you do normally in the classroom, do them in this online setting as well. All right. So we have introduced a discussion of the new type of, it's not new in itself, but it's new to us, new type of transport, and that is heat transport. Now, we don't measure heat itself. One thing that we can measure is temperature, and this heat transfer is going to happen essentially if we have differences in temperature, and then those differences in temperature will try to equalize. So basically, if I have, this is just the simplest case of them all, if I have a slab of a material, nothing's flowing for now, though normally we are interested in fluid flowing. And basically I have it has thickness Y, there's an area on top A, and I keep top and bottom at different temperatures. Presuming that this bottom temperature T1 is larger than T0, then I'm gonna have some heat transfer going on in upwards direction. If I set it up in a coordinate system, this upward direction is Y, and I'm going to flow, the flux will happen from the higher temperature to the lower temperature, and basically, so it's gonna be in Y direction. And basically, then the simplest model for this to happen is that the flux per area, we always have to normalize fluxes per area, is proportional to the difference in temperature, delta T, and inversely proportional to the separation between these two spots. And the coefficient of proportionality is thermal conductivity K. What this will also happen, so this is going to be T1 minus T0, and since basically I'm always flowing from higher to lower, and every coordinate system we know points from lower to higher, we have to have that traditional minus in these relationships. So when I actually put this in coordinate systems, then the derivative, the Y component of this linearized heat flux, Qy, is negative K times the derivative of T in the Y direction. Again, because derivative of T lives in coordinate system and aligns with it, but every coordinate system points from lower to higher. We actually have to have that minus to make things physically right, because they flow from higher to lower temperatures. If I have a material that is kind of behaving the same in all directions, then this will happen in every direction, and my coefficient of proportionality, K, will be the same in every direction. So we're going to have that Qx is minus K dt dx, Qy is minus K dt dy, and Qz is minus K dt dz. So when I put that together as a vector, I can recognize that dt dx, dt dy, dt dz are components of the gradient of T in Cartesian coordinate system. And then these are my x, y, and z components of flux. So flux is a vector, and it's proportional to the gradient of T. So this is actually a much simpler relationship than the one that we had for momentum transport, because in momentum transport, we had differences in velocity. Velocity in itself is a vector. So basically, to look at where all of the differences in velocities can happen, we need to have a tensor 3x3 components. Here, all I need is gradient of a scalar field of temperature. So that part is simpler. Now, if I had an anisotropic case, in general case, this thermal conductivity could be a tensor that is multiplying a gradient of T, but we're not going to deal with such cases in this course. This is just for your general education. Now, when I look at the units are, so basically I'm going to look at this relationship to recover what the units are. And when you do the little the little calculation, watt is joule per second. So this is unit of power divided by meter and Kelvin, which is temperature. Now we can also normalize thermal conductivity. If I normalize it by density and the thermal capacity of the material, then I'm going to get a normalized thermal diffusivity. And the units of that are meters squared per second, which are the same as kinematic viscosity, so they can be compared, and that's going to be actually one of the comparisons we're going to make. Now, one thing that I mentioned is that the big problem is that if fluids come in, so if fluids come in, they can basically help with the heat transport, but there's also momentum transport going on. So this is where I start coupling the two types of transport, and that is essentially mathematically pretty complicated. Now, so basically, if I have fluids, we typically have a static coordinate system. So I'm sitting in one spot, and as my fluid is flowing, right, every time it's flowing, it's pouring in different fluid, different actual molecules that I'm actually looking at, or the unit volume of the fluid is different at different time, and we have to account for that. So we accounted for that already even in momentum transfer, because essentially that different unit of fluid can bring in its own momentum. So in order to see what's happening, not only that I have to look at the friction in between the layers of fluid within one fluid unit, I have to also look at what's carried in. So that bulk motion, if I think about it, first I have to quantify energy. So right now, this is essentially energy transfer. So we have to quantify energy that is in that fluid unit. And we do that. This is, you know this from thermodynamics, so it's really just a brief review. My kinetic energy per unit volume is quantified by 1/2 rho v square. So basically my v square in Cartesian coordinate system is given by this. My internal energy per unit volume, I'm going to have a little hat to normalize it per unit volume, is basically rho u, normalized internal energy. And then let me move this from the video. All right, excellent. So no, Zoom has some ideas where my video, I'm trying to adjust so that I'm not, so that my Zoom control is not over the slides. So basically, rate of energy per unit area carried across a volume size. So if this is my little coordinate system volume unit, then I'm going to look at, so if this is X side and this is X side, what's carried across this side is basically done at the rate of Vx, because this is the projection of velocity onto this X side is essentially Vx. So this is essentially the total energy that is carried by the unit of fluid, and it's carried at the rate Vx. Comes in through this side, and of course leaves on the other end. So we will have to multiply by area to get the total that is coming in and out of this volume unit. So this is just an example in X direction. This of course has to be repeated in all of the directions. So we're gonna describe this convective portion of the energy flux with the vector, but basically takes the energy and multiplies it by vector v. And if I need to project it on any general surface, I can do so by multiplying with the, by doing the projection on the normal of that surface and times the surface area. And if I need to collect all of those, I'm going to sum up or integrate, right? So integral is really sum. Now, there's more work that can be done. So this is just stuff that just literally flows in. It's literally carried in. There's more heat sources in there. And some of them are basically because of the friction between the layers of the fluid. There is work that fluid is done simply by its molecular that is doing by its molecular motion. So let's try to quantify those. So in thermodynamics, we know that the change in internal energy is equal to the heat added to the system by molecular or convective mechanisms, plus the amount of work done on the system. And in this case, we're going to look at the work done by molecular motion. Okay? So work in general is force dot displacement vector. So if we have force vector F and displacement vector R, this is basically the path along which work is happening, then force dot R, this is the dot product that basically projects and makes sure that we are only really the component of the force that is parallel to the path of application will actually do work. So that that makes sure. So you can either find that component of force and then just multiply it, or this is formal general definition. So this projection will take care of that. Now, the rate of work or power is derivative of work. So if I actually take the derivative and my application of force is momentarily constant, then we are actually going to get that F dot V there is the rate of work. So basically V is my velocity. So I can get the power by projecting my force onto velocity. All right, now in this particular case, when I'm looking at the molecular mechanisms and those that are actually source of viscous forces, not just viscous forces, but overall all of the molecular forces, we have quantified that by, this is hydrodynamic, the hydrostatic, the general thermodynamic pressure. Okay? So this is constant P times identity tensor, plus the tensor, our good friend from momentum transfer, tensor tau, that basically quantifies shears and viscous stresses. Now, in this particular case, the way we're going to then quantify work done by the forces in this case is by projecting them in similar manner to this onto velocity. Now, this is a little complicated looking, or it's packed inside. It's simple looking, but simple is deceptive. This is a tensor. So this is really what this comes down to find. So normally if you had a force that is just a vector, you know how to do vector dot vector. Now, your stress tensor is a combination of at least 3 vectors in 3-dimensional system. So basically you can dot one by one of it. So when you're looking at the stress tensor, the way you do matrix vector multiplication, you're going row dot product the vector itself, right? So that's how you will actually get components of this. So you will really multiply a matrix that describes this tensor with a vector. And that works because the tensors we're looking at are symmetric. So in any event, just think about it as this as matrix vector multiplication. So now what I have is a combined energy flux. The first flux Q is the one that I described by Fourier's law. That's the one that sits there always, regardless of whether my material is fluid or not, and whether it's moving or not. Okay? So this one I have all the time. And come testing time, you will be focused on, hey, if this is all, that's great. That's simple to deal with. If it's not, if I actually have fluids flowing, then I have to account for this portion, which can get a little bit hairy, or there's quite a bit to account for. So I have to account for the work of the molecular forces as well as the energy simply carried into the fluid by convection. Okay, so this is, but this is my vector that describes everything that can basically come in and out of my control volume. Now, I'm no need to go into details, but the details are here if you want them. This can be also written slightly differently by involving enthalpy. So if I break down my molecular stress tensor in the pressure part and the viscous part, and then add the pressure part into the other one. We can rewrite this again. I'm not going to go into details, but this is more practical for calculation, is to look at the first part, not as the total energy, but just involve enthalpy here, and then just look at the work of the viscous stress tensor here, and not the total molecular stress tensor. So the pressure part just kind of jumped into here. Now this is easier to calculate. This is easier to conceptualize, because this is just the total energy carried in, and then the work of the molecular, all of the molecular forces, and the Fourier transfer heat flux. This is the one that's happening simply because of the differences in temperature, everything else being absent. So I'm going to stop here for a moment. Questions about this formula? I know that I threw at you quite a number of vectors and tensors and whatnot, but is it conceptually clear what is going on? And if not, what is the question that you might have? Anyone? Everything is clear? Your coffee is strong enough, or whatever it is that you need to wake up on Monday morning?
Can you go back over the multiplication with the molecular stress tensor?
This one or this one? The second?
Yeah, that one.
So is the rate of work, is this formula clear? This is the basic, this is review of the, where we did this in physics, I presume, or if not, then in thermodynamics. So if I have a force acting along a path, work is given by dot product of the force vector and the displacement vector. Is this clear?
Yes.
Okay. So then if I'm looking at the rate of work, and what I'm looking for is this energy flux. Flux is rate of work and also per area. So when I'm looking at fluxes in general, I'm looking per time per area. So now I'm looking to quantify work per time per area. So first, if I look at the work per time, okay, conceptually, that's essentially simply a force dot velocity that the object is moving with. Is that clear? This is just from mechanics, right?
Yeah. Yes.
But now I have fluids. So this velocity is a complex thing in fluids, the velocity field. It's not just like one object moving at a constant velocity, in which case I could just use a formula like this. It's not one object, it's this fluid, and fluid has fluid layers, and those fluid layers are rubbing against each other and whatnot. So this is that whole concept of the viscous stress tensor that was needed to describe all of that, right? I mean, in essence, our Navier-Stokes equation, however complicated looking, in essence, it's a Newton's law. F is equal to mass times acceleration. It's just that quantifying all of those things in the presence of different fluid layers moving is complex. So that's why we actually needed these stress tensors. Now, so basically, I don't have just simple force dot V. That's what, this is what I'd love to do for some area, but I can't do that. I have to actually use those, the stress tensors that we have described in our momentum transfer lecture, and that was done by this P, if you remember from before. And this was, again, this was an identity matrix times P. So this is just pressure along diagonals, and this is my full-blown shear stresses with all of the components, 3x3 tensor, right? So basically, what used to be a simple in mechanics, just a force, you know, moving a piece of something, like let's say that I'm moving this cup, right? That's not as simple anymore if I have fluids involved. So I have to describe stress in this case is just the force per area of contact, right? Well, in fluids, I gotta involve the stress tensor. So basically that stress tensor is right here. So instead of just doing F dot V, I have to have now stress tensor essentially multiplying velocity. Okay. So this is a vector, and this vector is the result of a stress tensor dot V is really just the multiplication of the stress tensor and V. Formally, it's really the the stress tensor transposed, but since the stress tensors we're working with are symmetric, it's the same thing as just saying this is the stress tensor times, this is matrix vector multiplication.
Okay, thank you.
Yeah. So this is a vector analysis and tensor analysis, but I find this, I can start from this I don't have trouble remembering. And I can generalize it to this conceptually when thinking about it. Otherwise, there's no way I can remember this, or I have to constantly look it up. So this is why I'm going through like this explanation so that you know. Ultimately, we will write down formulas that you will just simply apply, but I'd like you to know the conceptual source of all of this. Because again, we just have to figure out what are the forcings in the fluid, and forces in fluids they're hard to quantify, and we need stress tensors. They're constantly changing and evolving to quantify them. So this is the way. So again, this is just think about F dot V. This is this is what it takes to do F dot V in a fluid. And this is just carried in. So this is, again, this is the energy per unit volume, kinetic plus internal. And this is what the unit volume has, and that's carried in by velocity V into my connect. And this is my energy flux that I'm gonna have to project this on all of the sides and multiply by area to actually see the total flux coming in and out of a volume. And we're gonna do that in applications, but I'd like you to understand how this came about. And
what are the units of flux?
Whatever it is that you're measuring, right? Per area per area per time. So in this case, basically this is what I wrote down here. This is energy, so joule per area per time. This is the units of this energy flux, this one, right? So that's how I got the units of K, thermal conductivity, is that it's units of this divided by units of dt dx. And units of dt dx are Kelvin per meter. So instead of dividing, I'm multiplying by meter per Kelvin. Is this clear?
Yes.
So flux of anything, now we're looking at energy flux, right? We used to have momentum flux. So flux, the way we are conceptualizing it in this, actually the entire, no matter which transport we're looking at, will be whatever it is that we're looking at. Right now we're looking at energy, okay? Energy per area per time. So rate of energy per area, if you will. Before this, in the previous part of the course, we had momentum. So there was momentum per area per time. Yes? All right. So is this formula conceptually clear? So this is combined energy flux that quantifies all of the things that could go in and out of my volume. Not all of them, well, some of them. We need to also add external forces that are outside of this. And we need to add any sources and sinks. Okay. So before we do that, I would just like to go over how these dimensionless numbers quantify the mechanisms, and a little bit just to kind of show what thermal conductivities could be, because that's what ultimately describes the materials we're working with. So one thing that we will have to be overall careful is, what is the transport that is dominant? So for instance, if you look at the differences in temperature that are driving the heat flux, there are all these, so that's basically what's quantified by Q over here. And then there's stuff that is happening in the fluid. Okay? It is rather important to know what is the really, is this 10 times smaller than this, or is this 100 times smaller than this, or is it the other way around? Because frankly, if I have different, if I have different orders of magnitude and they're like 2 times different, then I can cut my calculations short and just ignore some of them. Essentially, even if I have large differences in temperature that are driving some basically Fourier law type of flux Q, if I have this very fast turbulent flow going through, who cares about those? Majority of heat is simply just flowing in. And all I have to focus on is figuring out the flow in and flow out. Versus, oh, do I have a very slow flow? And I can basically ignore anything that is happening here and just focus on this Q. So that's something that is very important for you as an engineer to develop that type of intuition, to look at every problem, even if we in textbook or in any kind of cases that we go through in courses, give you sort of examples of these situations, but you as an engineer will deal with a new situation. And in that new situation, you need to be able to evaluate what is the dominant mechanism, what is worth calculating first, and then you can focus on details as necessary. So one of those numbers is Prandtl and Peclet number. Prandtl number basically looks at momentum versus energy transport. And this is just looking at the kinematic viscosity and dividing it by thermal diffusivity. Both have the same units. They're meters squared per second. If you remember thermal diffusivity, I got from thermal conductivity by dividing or normalizing thermal conductivity by rho and heat capacity, so density and heat capacity. So that's something that gives me the relative number of these, so I know what to focus on. And the worst problems are those that actually have a Prandtl number around 1, or basically meaning that both of these things are important and you have to calculate both, which can get complicated. Now there's also Peclet number for heat transfer. This is basically just multiplication of the Prandtl number and Reynolds number. So that basically gives the bulk flow advection of heat versus temperature gradient. And that's this example that I described, that if things are high Reynolds number is heavily turbulent flow. If things are moving in real fast, that's gonna overcome any kind of just minor differences in or the heat flux due to some differences, local differences in temperature. So we're going to look at some common values, and they're available in tables in BSL. Normally these values are tabulated, and we're going to look at them at different for different materials, so gases, liquids, and solids. So for instance, everybody just take a piece of paper and pick your gas, pick a gas from this table. And what I want you to focus on is what happens to thermal conductivity, K, and again, it's watts per meter per Kelvin. So what happens to thermal conductivity with temperature increase? So here we have, for instance, in some cases we have 2 values, in some cases we have 3 values. So then I'm gonna pick on somebody I haven't heard from. And heard from Erlinda, James, and Ruben this morning. Let's pick on somebody who is here. And I've heard from Adrian. So Hugh, are you there? Mr. Kong?
Yes, I'm here.
So which one do you pick to look at?
Hydrogen. You said what the K versus T behavior is, right?
Yeah, so I'm asking what is happening to thermal conductivity as I increase temperature.
Oh, I wrote down that they're directly proportional.
Directly
Positively.
proportional. So basically, so which one do you pick to look at?
The hydrogen.
Hydrogen. All right. So basically here, so my K seems to be increasing as I'm increasing temperature, right?
Yeah.
Okay. Something to also look at is the Prandtl number, just in terms of within this material. Is my momentum, or so basically this is the momentum versus or divided by heat transfer, okay, in terms of the molecular motion. So I can see that this is roughly 0.7 for gases. So they're give or take, it's relatively close to 1. It seems that the momentum is going to transfer slightly slower than heat, right? And this is just for intermolecular reactions, but they're give or take on the same level, if you will. All right. Now, if I have some liquids, again, I'm gonna take a moment and tell me what is happening with a liquid that you pick from here. And I'm gonna pick on somebody to wake them up. So Amina, are you there?
Yeah, I'm here. So
So-
for pentene, it looks like it's decreasing as the temperature is going up.
So this is similar to, if you think about viscosity is decreasing as well, right? So thermal, the conductivity is decreasing. So this is sort of, if you think about heating up, so honey, if you heat it up, it's gonna flow faster. Oil on your pan when you're making breakfast, I hope you managed to do that this morning, then it's gonna basically, viscosity will go down, but it seems that thermal conductivity will go down as you heat up. So that's kind of important to find a way to remember that. It doesn't have to always be the case, I think. Is it the case for all of these? It seems to be in this table for all of these liquids, there, as you heat them up, the thermal conductivity will go down too. So one thing that is important is that in a lot of cases, we are going to look at, so in momentum transfer, we used to take viscosity, especially for Newtonian fluids, as constant. Even though we know that viscosity actually changes with temperature, but since we weren't changing temperature, then we could take viscosity as constant. It's quite important to actually think about here, because we're going to talk about heat transfer. Heat transfer happens because of differences in temperature. So this is non-isothermal. This is not, there's no isothermal transfer anymore. So technically our thermal conductivities could change from location to location simply because I have different temperature. Now we're going to assume that temperature differences are not high enough, or that we can freeze this thermal conductivity value for the moment. But that's an assumption. It's a simplification for solving the problem. So you should be aware of that. And specifically, you should be aware of that in applications in real life, because in petroleum engineering, thermal temperature changes can be quite extreme. And therefore you kind of, those assumptions never really hold, but we use them anyway for simplified calculations. Okay, so something to think about. Now, just to look at who can transfer faster, momentum or heat by molecular motion. Basically, momentum transfers faster in liquids. So we can actually see that now we almost have, these numbers are almost 10 and sometimes above 10, or even super high. So basically that means that the momentum transfer is going to take over in terms of molecular mechanisms over the heat transfer. So it's somewhat more prominent. And finally, solids. So if we look at the solid behavior, thermal conductivity, I'm just gonna now comment it on myself. I picked on you enough. So let's look at aluminum, for instance. Again, as I increase temperatures, so note the temperature increases that matter for solids are much higher here. And this is almost close to a melting point, it seems. A lot of, in this range, a lot of metals will start being soft at least. So basically we will actually have increase in thermal conductivity. So this is something that follows the similar rule. And it seems that I'll pick one more. Let's do steel. Steel will somewhat decrease. So this is, so it's not always a rule. So remember simply to look these up. Okay, so not only that we have different thermal conductivity behavior for different type of materials, we also have to, in the business of porous media, we have at the very minimum one rock or one solid phase and one fluid phase, and that's quite frankly, if we're lucky. Now, we wouldn't be in the porous or petroleum engineering business if we weren't looking at multiple fluids. We would like oil to be there all the time, but you cannot really avoid the presence of water. So at the very minimum, you have one solid and two fluids. Now, in those composite systems, and they're not just composite, it's not just like a slab of oil next to a slab, whatever a slab of oil means, but basically it's not like a beaker of oil next to a beaker of water. We have them in a very complex neighborhood relationship in a porous medium. So in a very simplistic description, such as given here, I have sort of inclusions, spherical inclusions. So let's say that I have oil filling in all kinds of glass or these glass spheres. How about that? Quartz. So essentially then I have thermal conductivity of this embedded medium and thermal conductivity of the medium surrounding it. So this is a simple there's a simple formula that gives me thermal conductivity of this composite, or rather effective conductivity. So however the complicated situation might be here, when I actually impose T1 and T0 and basically measure the heat flux going through, possibly this pretty complicated medium, we can measure effective thermal conductivity by simply comparing this heat flux to Fourier's law. So Fourier's law will basically say Q is minus K gradient of T. So I can measure gradient of T is something that I measure. Flux Q is something that I can measure as well. So basically that gives me effective K, however complicated this medium inside might be. But it's also, of course, useful also to break down this effective medium in terms of the K0 and K1 that we're describing these inclusions and the medium around them. So basically for this composite, actually there is a formula in this particular case. It's actually called Maxwell's formula that gives you, this is the volume content of, I believe, of K1. And this phi, so this is volume fraction of K1. And then this formula will give you what the effective effective thermal conductivity divided by K0 is in this particular case. This is something that resembles porous media that we deal with, specifically granular materials. However, we also have to understand that there will be a major shift in this value of K effective if these spherical inclusions actually touch. And in all of the applications that we care about, they do. So we will have basically a compacted granular medium where all of the, it's a close packing of spheres, and those spheres touch at multiple points. And once those spheres or this spherical inclusions start connecting, they also can effectively transfer heat. And if I'm thinking about heat transfer, if these were actually solid inclusions, thermal conductivity of solids is much higher than it is of other fluids. So once they connect, this effective thermal conductivity will also jump in a value. So this formula is not necessarily good unless I have this disconnected inclusions. Another applications could be foam or emulsion. So in emulsion, I'm going to have droplets of different liquid inside another liquid, and essentially I can get the effective conductivity of an emulsion that I might be injecting into my porous medium. All right. So just as a comparison, what we had in a momentum transfer, we're looking at the potential differences in velocity, and driving force was the gradient of velocity. This, since a gradient of velocity is a tensor, so that gives us flux expressed as stress tensor, tau, and the transport coefficient in simple cases was viscosity. And in some not so simple cases, we looked at effective viscosity. Now, transport quantity in heat transfer for heat it's essentially energy transport, but we're quantifying it by potential differences in temperature, or that's our driver. So if I have an existing gradient in temperature, there will be heat transfer. Okay? Now we're quantifying things with heat flux, and we're often referring it to Q, and more generally, when we have the coupling of the two, there is that energy flux E. And transport coefficient, that is basically coefficient of proportionality that relates the heat flux to the gradient of temperature, is thermal conductivity K. If you remember, viscosity of gases at low density increases with increasing temperature. For liquids, we actually had that it decreases. And similar is happening with thermal conductivity, but it is important to remember that this increase or decrease, especially with liquids and solids, is not necessarily always there or the uniform. So always look it up for the particular liquid or solid that you're looking into. And we will now, well, we will have to actually stop. So that's actually a great point to stop. So next time, we will start with shell energy balances as well as the first example. So we're going to actually start now solving for the rest of the week. We will be solving problems. So we will introduce how we do boundary conditions in these cases. And I'm just going to hint that boundary conditions will again differ quite a bit, depending on whether materials that are in contact are similar or not. In terms of thermal conductivity, and we will do the shell energy balances to actually solve some problems. All right, well, this is where we're going to end today's lecture. Now, let me know if anybody is, or I'll just stay on for a while if anybody wants to stay on for the office hours. Have you started working on homework? I hope you have. Min has sent a reminder last time. So we will be asking you to solve your homework by hand and then scan and send a scan solution to Min, or they're uploaded to Canvas. Now, at the very minimum, it could be done by phone, or it could be done also by the camera on your laptop. It can take snapshots as well. So between the two, figure something out that works for you if you don't have a physical scanner that can scan it into PDF. Questions? Okay, if there are no questions, again, I'm going to stay on for our office hours, but otherwise, I see you on Wednesday. And I'm going to figure out where to stop recording. Stop share. And stop recording.